We have covered the Earth with massive megacities and learned to build skyscrapers almost a full kilometer high. But have you ever wondered where that absolute limit really is? How high can we actually build before the planet itself gives us a firm no? At first glance, it seems like all you need is to pour a wider foundation, use more steel, and you could reach all the way to the moon. But in practice, everything is much more complicated. Up there, at enormous heights, the familiar laws of physics simply stop working the way we expect. Nature itself begins to fiercely resist our intrusion, setting traps that ordinary builders do not even suspect. Today we will explain why all the money in the world would not let us build an extremely tall building. We will show you the limit of human possibility in architecture. And we will reveal the secret of which insane technologies of the future may one day allow us to deceive gravity itself. At the beginning of the 21st century, engineers in Dubai set out to do the impossible. They decided to build a structure that would pierce the clouds and rise to a height of 828 meters. It was the Burj Khalifa. When construction was just beginning, many experienced architects believed the project was doomed. Harsh winds blow in the desert, and the sand makes the ground extremely unstable. Builders had to drive almost 200 concrete piles into the ground, each 50 meters long, just to keep the enormous building from sinking under its own weight. But the main threat was waiting for them above. At heights of more than 500 meters, the air behaves completely differently than it does on the ground. Up there, incredibly powerful air currents rule with the force of a hurricane. If you go up to the very top floor during strong winds, you will feel the entire building swing from side to side by 1.5 meters. This is not a mistake by the builders. This is harsh reality. If the tower were completely rigid, the wind would simply snap it in half. Engineers had to make it flexible so it could yield to the elements, like a tree in a storm. When the tower was still rising, the internet was full of the darkest predictions. People were sure that with the very first strong storm, the top of the building would simply break off and fall onto the city. Theories appeared claiming that giant secret mechanisms were hidden inside the tower, huge pendulums weighing thousands of tons, artificially keeping the building in balance. Some even claimed that classified alien metal alloys had been used in its construction because ordinary steel supposedly could not withstand such colossal pressure. People simply did not believe that classic materials could work at a height of almost 1 kilometer. There are no secret metals. The engineers of the Burj Khalifa fooled the wind with pure aerodynamics. If you look at the tower from above, it resembles a flower with 3 petals. This stepped shape was not made for beauty. When a smooth stream of wind hits a flat wall, it creates huge vortices that begin to shake the structure. But the uneven sections of the Burj Khalifa, each at different heights, cut the air currents into small, chaotic streams. The wind simply gets confused in these edges and loses its destructive power. However, this design has one hidden limit that few people think about: the elevators. Ordinary steel cables that lift the cabin become too heavy. At a height of 600 meters, a steel cable begins to snap under its own weight. That is why, in super tall buildings, you cannot make one elevator from the first floor all the way to the very last one. You always need transfers. But if wind stops us from building thin, tall needles, why not build a huge, wide, artificial mountain that would be more stable than any skyscraper? In 1995, Japan faced a serious problem. The population was growing, and there was catastrophically little space on the islands. The capital was overcrowded. And then a group of bold designers proposed an incredible concept called Exceed 4000. It was not just a high-rise, it was a real steel volcano. The project envisioned building a structure exactly 4 kilometers tall. It was supposed to be higher than the real Mount Fuji. Inside this colossal pyramid, exactly 1 million people could live and work comfortably. It would be a fully autonomous city with its own parks, clouds inside the dome, shops, and weather systems. Just for this structure to stand in place and not fall, its base would have to reach 6 kilometers in width. The project was so grand that building it would require more steel than the entire world produced in several years. Such scale frightened the public. Many believed it was a shelter project for the richest people on the planet in case of a global catastrophe. Rumors spread that such a huge structure would inevitably change the climate in the region, create a permanent shadow over the rest of the city, and trigger endless rains because it would block air masses coming from the ocean. Some pseudoscientists claimed that the giant metal mountain would become a huge magnet for all lightning and cause disruptions in Earth's electromagnetic field. It seemed too ambitious, too frightening, and completely unrealistic. The Exceed 4000 project was indeed never built, but not because of fear of climate change. The main reason lies in the incredible mass of the entire structure. Even if the base were made 6 kilometers wide, the weight of millions of tons of steel and concrete would not disappear. If such a building were erected on ordinary ground, it would literally begin to press through the Earth's crust. The soil beneath it would not withstand it, and the base would start to sink, deforming the planet itself in that place. The building would have to be constructed right in the ocean, resting on incredibly deep and solid sections of the seabed. And even then, the logistics of moving 1 million people every day would destroy any economy. Steel and concrete had reached their absolute limit. They are too heavy. We need something completely new, a material that would be lighter than fluff, but stronger than diamond. In 2004, 2 scientists in a small laboratory were doing something very strange. They took an ordinary piece of graphite, the very same material used to make the cores of simple pencils, and stuck ordinary tape to it. Then they peeled the tape off, removing a thin layer of graphite. They repeated this process again and again until the layer on the tape was only a single atom thick. What they obtained turned world science upside down and brought them the most prestigious scientific prize. They discovered graphene. This is a material that looks like an invisible mesh, similar to a honeycomb. Soon, based on it, scientists learned to create carbon nanotubes. If you roll a layer of graphene into a cylinder, you get a thread that is 200 times stronger than the best steel, while weighing 6 times less. It seemed like this was the solution. Just take it and build towers all the way to the moon. The discovery triggered a storm of imagination. People online began writing that within just 5 years, all old houses would be demolished and invisible cities made of graphene would be built. Rumors appeared that the military was already making invisible tanks and impenetrable suits from this material. Science fiction fans claimed that the problem of high-rise construction had been completely solved, and now we were limited only by money. People thought graphene could simply be poured into molds like ordinary liquid concrete, creating indestructible walls tens of kilometers high. Reality turned out to be much more complicated. Graphene and carbon nanotubes really do have fantastic properties at the micro level. The problem is that we still do not know how to make large objects from them. In laboratories, scientists can grow a nanotube a few centimeters long, or in the best case, a couple of meters. As soon as we try to weave these microscopic threads into a thick cable or create a strong beam, the material loses its incredible strength. The threads begin to slide past each other and the structure falls apart. Producing even 1 kilogram of pure nanotubes costs an enormous amount of money. We are still at the experimental stage. But while supermaterials remain hidden in laboratories, engineers have come up with an insane plan to deceive gravity itself and make a building stand without a strong frame. At the end of the 20th century, when it became clear that ordinary materials would not allow us to build a tower all the way to space, researchers turned to a very unusual concept. It was called the space fountain. Imagine an incredible structure, a tower rising to a height of 20 kilometers, but with no thick load-bearing walls, no deep foundation, and not resting on the ground with all its weight. It stays in the air thanks to constant motion. This sounds like pure magic. No one in their right mind would finance the construction of a building that technically hangs in the air. The concept seemed so detached from reality that for a long time it gathered dust in archives only as a theoretical experiment for physics students. When information about kinetic towers became available to the general public, many people decided it was a joke. Popular magazines wrote that it was an attempt to create a perpetual motion machine, that it violated all known laws of physics. Conspiracy theorists claimed that such technologies used hidden Earth energy or anti-gravity, which government agencies were keeping from us. It is impossible to imagine a huge skyscraper made of metal and glass being held up by something invisible. This is not magic and not anti-gravity. It is pure kinetic energy, which we call active support. The principle is very simple. Imagine taking a water hose and pointing a powerful stream straight upward. If you place a light plastic ball on that stream, it will hang in the air as long as the water keeps flowing. The space fountain works the same way. Inside the tower is a hollow tube from which all the air has been pumped out. Millions of tiny magnetic capsules are fired through this tube at tremendous speed. At the top of the tower stands a powerful electromagnet that turns these capsules around and sends them back down. The force with which the capsules strike the upper turning mechanism pushes the tower upward, overcoming gravity. The tower stays up because of the constant flow of these particles. But this brilliant solution has one fatal flaw. If the power in the entire complex suddenly goes out and the magnetic guns stop, a 20-kilometer tall tower will collapse to the ground in a matter of minutes. We have fooled physics, but we have forgotten the main problem: the people who will live in these towers. Even if we build a tower 10 or 15 kilometers high, using active support or materials from the future, an unexpected obstacle is waiting for us: the human body. Back in the 19th century, brave balloonists tried to rise as high as possible in hot air balloons. They took warm clothes with them, but they did not know the main secret of the atmosphere. When they reached an altitude of 8 kilometers, they began to feel a strange euphoria. They wanted to sing and laugh, and then they simply lost consciousness. Many of those early flights ended in terrible tragedy. At that height, the air becomes incredibly thin. There is just as much oxygen there as on the ground, but the pressure is so low that our lungs simply cannot absorb that oxygen into the blood. A person slowly and silently falls asleep. People often think that at high altitude a person freezes in the first second, or that because of low pressure the eyes can literally burst. Hollywood films have taught us that depressurization at a height of 10 kilometers leads to instant and terrifying consequences, with people being sucked into tiny holes. Viewers are sure that life in a super tall building is impossible, simply because clouds are toxic and radiation from the sun will instantly destroy everything alive through the windows. Hollywood exaggerates, but the essence remains true. Above 8 kilometers, the danger zone begins. If you open a window on the 100th floor of a 15-kilometer tower, you will lose consciousness in 3 minutes. And at a height of about 19 kilometers, there is the Armstrong limit. The pressure there is so low that liquids in the human body begin to boil at the normal temperature of 36 degrees. A building of this size would have to be sealed like a submarine or a spacecraft. Any crack in the glass would lead to a catastrophic loss of pressure. In addition, the elevators in such a building would have to move at 20 or 30 meters per second. Because of such a sharp pressure jump, passengers' eardrums would not hold up. There would have to be hours-long stops for acclimatization, just like climbers make. It turns out that building upward, resisting gravity and weather, is too dangerous for the people themselves. But what if we changed the rules of the game? What if we started building not from the bottom up, but from the top down? Back in 1895, the Russian scientist and dreamer Konstantin Tsiolkovsky was looking at the recently built Eiffel Tower. It inspired him with an idea that was a full century ahead of its time. He imagined a tower that would not grow from the ground toward the sky, but descend from space down to Earth. This is the concept of the space elevator. For a long time, the idea existed only on the pages of science fiction novels. The essence is to launch a huge satellite into geostationary orbit to a height of about 36,000 kilometers, and then slowly lower a strong cable from it straight down to Earth's equator. Once the cable touches the ground, we anchor it. Cabins with cargo and people could then travel along this cable, powered directly through the line. No rockets, no explosions, just a smooth ascent to the stars. When people began talking seriously about the space elevator, many scientists were horrified. Skeptics claimed that such a long cable would work like a giant whip. If it suddenly snapped, it would wrap around the Earth several times at high speed, destroying continents and causing global devastation. Others believed the cable would cut airplanes in half, or that it would alter the planet's magnetic field. People were afraid of the idea that a thread 36,000 kilometers long would be tied to the planet. The fears about a giant whip are exaggerated. If the cable snapped near the ground, centrifugal force would carry its upper part into open space, while the lower part would fall safely, because it would be made from the lightest materials. The principle of the elevator itself works through balance. The counterweight satellite rotates together with the planet, and centrifugal force pulls it away from Earth, while gravity pulls the cable downward. The cable always remains stretched tight, like a string on a guitar. The main problem is space debris. Millions of fragments from old rockets are flying in orbit. Even a small nut moving at tremendous speed could cut the cable. We would have to create a protection system or learn to dodge debris by shifting the base of the elevator. The space elevator is an incredible engineering challenge, but it is only the beginning. If we can anchor one cable from orbit to the ground, then we can go even further and wrap our entire planet completely. The absolute limit of human engineering thought is not a tall building. It is an orbital ring. In 1982, physicist Paul Birch published a series of papers in which he described this structure. It is a giant hoop built directly in space, completely surrounding Earth. This ring hangs at a height of several hundred kilometers. Thousands of elevators and cables descend from it to the surface of the planet. In essence, it is a huge ring road in space, along which millions of tons of cargo could be moved to any point on the planet in a matter of hours. This is a project on such a scale that carrying it out would require all the countries of the world to join forces. It sounds like the plot of a science fiction film. Many critics claimed that such a ring would block the sun, creating an eternal winter at the equator. They argued that the enormous mass of metal in the sky would inevitably fall to the surface because of gravitational disturbances from the moon or because of the slightest error in the calculations. People thought it was impossible to balance a structure 40,000 kilometers long. It was seen as a utopia that humanity was still thousands of years away from. An orbital ring would not fall because it works on the principle of active support, which we have already discussed. Inside a huge tube around Earth, a superconducting cable moves at incredible speed, faster than orbital velocity. Through electromagnetic forces, this cable pushes against the outer shell of the ring. The outer part can remain completely stationary relative to the ground. Research bases, factories, huge solar farms can be attached to it, and cables can be lowered down. This does not violate the laws of physics. It requires an enormous amount of energy and materials, possibly mined from asteroids. We began with towers that fear the wind and studied concrete and steel. We searched for salvation in carbon tubes invisible to the eye and tried to hold buildings in the air with magnetic guns. We understood how fragile humans are in the face of the atmosphere. In the end, we went out into open space. The limit of how high we can build is not defined by the laws of the universe. That limit exists only in our technology and in our determination. Perhaps one day we will look up and see not an empty sky, but a bridge leading straight to the stars.